Hello, this is Mr. Dobson and this is my fourth video on gravitational fields. This is Gravitational Potential 2, looking a little bit further into the idea of gravitational potential. Now, a little recap. In the first video we looked at the strength of gravity, or the force on every unit of mass, the force per unit mass, the force on every kilogram of our mass at the surface of the Earth, which we defined as little g, 9.81. In the second video we looked at Newton's equation, and we had a general formula for the force between any two masses anywhere in the universe, and then we sort of combine the two in a way. We turn this into a big M and little m situation where you've got a large mass and a small mass, and we redefined G with this more general equation that would work for any value of M, and R therefore would work for any planet. In the last lesson we looked at how gravitational potential energy changes, and we said if we want to move something up in a gravitational field we have to do work, and we defined that the work we would need to do per unit mass, if we take the M over to this side, is defined as something called gravitational potential, V, capital V, and we gave a formula for that gravitational potential is equal to minus Gm over R. So this is a very similar equation to this, as you can see, but you can see this one is R squared. For V it's over R. So that's where we got to at the end of last lesson. Now we're going to look at some of the interesting things that came out of the end of last lesson, where we said that when you calculate this value of V using this equation here for Earth, you get this negative number, minus 63 megajoules per kilogram. We also said that the book describes V as the work done per unit mass to move a small object from infinity to that point. Seems a bit of a strange way of putting it as well. So we need to try and understand what's going on there. So to do that, first of all, we're not going to think about the Earth. We're going to think about a simple situation of some kind of surface, and we have something held above that surface here. And we know, simple GCSE physics stuff, that if I was to put this on the surface here, it'd have no gravitational potential energy relative to the system. We know in real life it would have, because if the Earth's surface disappeared it would just fall through. But as less, at least here. And if I was to move it up some kind of heights, let's call this H, then it would then gain gravitational potential energy. It would have more, or an extra gravitational potential energy than it had when it was at the bottom. We also know that if we was to now release this object, it would immediately start to fall down. And simple key stage 3 physics that we would have done would tell us that, well, what's happening there is the gravitational potential energy is turning into kinetic energy. Okay, so we're gaining some kinetic energy by the fact that we're losing gravitational potential energy as we go down. So the idea is that we get some energy out of the ball in the form of kinetic energy as the ball moves towards the Earth. So we're going to gain some energy as we get closer to Earth. That's the idea I want you to take from that bit. Now consider the Earth, and we said that if we was to consider the gravity of the Earth, and we was to draw a graph showing how gravity of the Earth looks, if we was to draw an axis here going on like that, then the value of gravity once you get to the surface it's 9.81, and then it drops off exponentially with distance. So as you move away from the Earth, that's not a very good exponential graph, let's see if we can do it a little bit better than that. As you move away from Earth, the value of the strength of gravity is going to fall. Now technically we know that exponential graphs never actually reach the bottom axis. There's always something there, but at some point we'll get to a negligible amount of gravitational field. So basically we'll get to a point where the Earth's gravity is now negligible. We don't really feel it anymore. But because Because it's an exponential curve, we actually tend to consider this distance as infinity. The reason for that being because actually it never really does touch that, it never really becomes zero. But if we could somehow get to infinity, it would be zero. So that's where we use this idea of infinity. So what we can say then is that at infinity, this distance away, if I was to put my ball here, there would be no gravitational potential energy with respect to Earth. So it would be zero. But what we just said in our discussion here said that as I was to move it closer to the Earth, or let go of it, once it's in the Earth's gravitational field, it would start to give me kinetic energy. I would start to get energy out as the gravitational potential energy went down, as it got closer to the surface of the Earth. So if I was to take my little object from this position here and move it this way, I can move it, I've shrunk it instead somehow, let's see if we can move it. Move it this way, I would get kinetic energy out. That seems a bit strange because I have no energy here, I have zero. So how do I go from zero and get energy out? Well, there is only one way mathematically to deal with that, isn't there? If I've got a situation where here it's zero gravitational potential energy, we know that the gravitational potential energy turns into kinetic energy, I know here, let's say surface of the Earth here somewhere, I have a high kinetic energy. Theoretically, if I let it drop all the way from out there, I've gone from zero kinetic energy here, and I've gone from zero to high here, and I know that my kinetic energy comes from gravitational potential energy, then I must have got this higher kinetic energy from gravitational, which means the gravitational potential energy at this point, if I can get my pen out, there we go, must be lower. So we have a lower value of gravitational potential energy at that point than at this point here. The only way mathematically we can resolve this problem to go from zero to a value lower is if we make the values here negative. So theoretically we have no gravitational potential energy when we are at an infinite distance from the Earth. As we move closer to the Earth, we move into negative gravitational potential energies. And where does that energy go? Well, it turns into kinetic energy as we move towards the Earth. So we have this idea that this will give us a negative answer, and this is where we get this negative gravitational potential from. So the idea as you move towards the Earth, it gets more and more negative. So this explains why, one, we have the negative value at the surface of the Earth, but it also explains why we have this standard expression or standard definition of what V is, as the work done per unit mass to move a small object from infinity to that point. What's confusing about that is the work done, normally we think of work done as us having to put energy into a system to make it do things. Actually, theoretically, to move from infinity to that point, we would get energy out. But work done is a change in energy, so it doesn't matter which way it's going. But obviously, most of the time, we're actually going to be taking something from near the surface of the Earth and trying to move it in this direction, in which case we'll need to do work, and therefore it makes a lot more sense. But the idea of infinity to that point, well, actually we would be getting energy out of the system. The idea is, realistically, that everything wants to go to the lowest possible energy state. So the lowest energy state is for an object that's out here. As soon as it starts getting close to the Earth and feels Earth's gravity, the lowest energy state is near the surface of the Earth because it has a lower value. So we've got a situation where we've got a change in gravitational potential energy. Now, as we said at the end of the last video, working in gravitational potential energy might work for when we're considering simple ideas we know from GCSE and taking it into a new situation, but actually for making calculations, not the best, because it relies on knowing the value of the mass that you're moving around the Earth, the test mass. Much better is an equation where we don't have to worry about that, and that's where V comes in, because V gets rid of our M factor for us, because it's the work done per unit mass. So this is why we tend to, rather than think about what value of GPE you'd have at different points away from the Earth, we actually think about what value of gravitational potential you have. So rather than gravitational potential energy, we look at what value of gravitational potential we have. Now we have a situation, for instance, a point here, a yellow dot, and that's visible. Let's try another colour. Get a nice bright green. Let's see how that works. There we go. Right, so we have a point here that is on the surface of the Earth, and the gravitational potential is minus 63. We have a point here where the gravitational potential would be 0. So there must be points along this path where the gravitational potential is various other numbers between 0 and minus 63. So we may have minus 50, minus 40, minus 30, minus 20, that's 20 apparently, minus 10, 0. Okay, so we have these, and minus 63 at the surface of the Earth. This is all in megajoules per kilogram. So we have these points where the value would be less. Because the Earth is round and the field around the Earth is radial, whatever I could say is true for an object this radius here would also be true, therefore, if that radius in that direction, and in this direction, and in this direction. So this value of 50 would, because it's all dependent on how far away you are, if we remember the equation, it's actually over r. G and the m don't change, because G and the m are the value of gravity and the value of the mass of the Earth. So theoretically, the r is what changes, providing the r remains the same. So anywhere where we've got the same radius, the value of v will be the same. So the potential will be the same everywhere, or equal everywhere, and therefore we give it the word equipotential. Now, because this picture is, as you can see, getting very complicated, one I made earlier, I've got a think net. There you go. So this is a picture showing equipotentials around the Earth. So we have this idea that anywhere, if I was to take a point anywhere on this line, the value of V at any of these points would be minus 40 megajoules per kilogram. The value here would be minus 30, and if I wanted to go from there to there, I would change my value of V, so my delta V would be 10 megajoules per kilogram. Kind of had space for that. So we have this idea. A more complicated view, but a more correct one potentially, is this diagram here, because this shows it shows the field lines. This is where we've originally started on this topic, with the idea of radial field lines towards the Earth, and it shows the equipotentials. What I like about this diagram is you can see the effect of the fact that it's divided by r. It's not exactly exponential, because it's not divided by r squared. It's not that kind of decay, but it is a curve, and so as you go away, it drops off. If we were to do gravitational potential, let me find a pen. So when we did G with distance, we looked at it being like this. When we do V with distance, it's much less pronounced, but it still drops off. The effect of that is that you see that the rings get progressively further apart as we move out. So we get further and further apart as we move out. So initially, not a big step to get a big drop, But as you go further and further out, it takes a much bigger step to get the same drop, because these are supposed to be drops of equal distance. So this would be a drop of 10, then another drop of 10, another drop of 10, another drop of 10, another drop of 10. You can see you're having to get further and further out for it to drop 10 each time. So another way to look at this is a sort of two-dimensional version of an image, but it's also possible to consider it three-dimensionally. If we think about looking at this and the side on, we can actually think about something called a gravity well. If this makes it more complicated for you to understand, feel free to ignore it. For me, I actually prefer this kind of measurement, this kind of way of thinking about it, as the idea that Earth is actually in a well of gravity. So anything that comes near that well of gravity will want to roll into it, and therefore will head towards the Earth. Bear in mind, this isn't like it's going to roll in a curve like that. It's just going to move towards the Earth. This is a representation of how the field strength changes over distance. And you can see, if we was to take measurements, this picture isn't ideal because it has the numbers going in the positive direction. They shouldn't really be negative. But if we was to mark lines of equal potential away from the Earth, let's make they're positive, they're at least equally spaced out, and then you was to draw down from these lines to put them in the other direction, you can see they start off close together, but as you move out they get further and theoretically further apart, somewhere out there. So we have this idea that as we move further out, the gravitational potential drops off at further distances. So we have this shape. So it's not just circle, circle, circle. If you ever draw a diagram like that, it's much more like this, getting bigger and bigger as we go out. So this is why it's negative. This is the idea of gravity wells, and this is the idea of why it's the energy required to move an object from infinity to that point. Now, it's quite a conceptual idea. You don't have to understand all of this perfectly. You do have to understand the idea of equipotentials, that these are lines of the same value of V, but you can understand that without having to really get all the concepts. Please feel free to look at other people's videos as well and stuff like that, because this isn't necessarily, I'm sure this isn't the best way to explain it. This is my way and how I get my head around it. But it is quite a conceptual thing that you may need to study up on a little bit more and listen to a few different people talk about it. But for now, that's the end of this video. Thank you.